Let's solve some problems on ramps. A 5 kilogram block, that's mass because it's in kilograms, is sliding down a ramp inclined at 28 degrees. So this angle here is 28 degrees. The coefficient of friction between the block and the ramp is 0.35, and that's the kinetic coefficient because this block is sliding. In the figure below, draw and label the forces acting on the block. Okay. We start with gravity. Gravity pulls from the center of mass, and it pulls straight down. mg. We also have the normal force, which is always drawn perpendicular to the surface of the ramp, or perpendicular to whatever surface the block is resting on. So the normal force has to lie along this angle, like this. Fn. Because they gave us the coefficient of kinetic friction, there also has to be a force of kinetic friction. And kinetic friction is always parallel to the surface. My arrows are not the correct lengths, but that's okay. We're not going to worry too much about that for now. Before I can proceed, I have to draw the components of gravity, because we're using these angled axes. Here's the tilted y-axis. Here's the tilted x-axis. Two of the forces, Fk and Fn, lie on the axes. mg is at an angle to the axes. What's the angle? 28 degrees. So I'm going to draw in this component and then this component. And if I were to take this horizontal, this x component, and slide it up, look at that. It's parallel to the ramp. This tilted x component should be parallel to the ramp itself. If this angle is 28, then so is this angle. So here, that's m times g times sine of 28, because this tilted x component is opposite the angle. For the y, I have m is 5 kilograms, g is 9.81, times cosine 28. Because this tilted y component is adjacent the angle, it forms the angle. Because I've drawn mg through its components, I can ignore mg itself. I've represented it already through the components. Okay, calculate the normal force. Well, the normal force, Fn, has to balance this force. And the reason is because the block does not accelerate off the ramp into the air, and the block does not accelerate into the ramp, crushing the ramp. So Fn has to equal or balance the 5 times 9.81 cosine 28. And again, the reason is because the total y force is 0. When we calculate, we get 43.3. That's a force, so the unit is newtons. Calculate the kinetic friction force. Well, the kinetic friction force is given by this equation. I've rearranged. Mu, we know, the value is 0.35. Fn, we found from above. So Fn is not equal, it's not equal to gravity, mg. It's actually equal to mg cosine theta, which is 43.3. And when you do plug in that value, use the unrounded version. And when we calculate, Fk is 15.158 newtons. Next, calculate the net force. Well, I know that the y forces all cancel. So all I care about is the x-axis. The net force is simply what doesn't balance out or cancel on the x-axis. So let me look at my x arrows. I have this 5 times 9.81 times sine 28. That's positive because it's to the right. The arrow points to the right, not to the left. But Fk points to the left. So that's a negative x-axis force. So let me put those down. I've got the positive mg sine 28, and then I have to add with it the negative fk, which I found above. And when I sum those up, my net force is 7.869577, which, rounding for 2 sig figs, is 7.9. I should round all of these other answers for 2 sig figs as well. Calculate the acceleration. I use Newton's second law, F net equals ma. I've rearranged, and when I plug in my net force of 7.86 ... and I plug in the mass they gave of 5 from above, my acceleration is 1.6 meters per second squared. Moving on, we have a similar scenario. I'll do this one quicker. Gravity pulls down. Normal force is off the ramp. And then there are these components. If the angle here is 17, then this angle is also 17. So this is mg sine 17, and this leg is mg cosine 17. Friction acts because they give me the coefficient, so there must also be a force of friction. The normal force balances mg cosine 17. When I plug in the mass of 6.4 kilograms, g is 9.81, cosine 17, what I get is 60.04, ... And I round that for 2 sig figs, so it's 60 newtons. Friction, kinetic friction. The force of kinetic friction equals the coefficient, mu, times the normal. So the coefficient they gave us as 0.21. I multiply by the normal force, which is this unrounded value here, 04, ... And what do I get for friction? Negative 12.6, ... Well, I should leave the negative out for now, which rounds to 13. Calculate the net force. On the y-axis, the forces cancel, so all I care about is the x-axis. I look back to my picture. I have this force acting on the x-axis and this one on the x-axis. So, of these, one is right, one is left. I add those up. mg cosine, sine, even though it's the x-axis, we're using sine here. And then I subtract the fk. Mass we have as 6.4. Sine 17. If you calculate that value separately, you get 18.356. And then you subtract away the kinetic friction, which is 12.60 ... And the net force, which is all on the x-axis, comes to 5.7477 ... We round it to 2 sig figs, that's 5.7. For the acceleration, we use Newton's second law, F net equals ma. And if I cross multiply, I see I do have Newton's second law. I've just rearranged. So we plug in the net force from above. It's this unrounded value, 7477, divide by the mass. And the acceleration is to 2 sig figs, it's 0.90. Here's the next problem. Like always, we have gravity pulling down. Here's mg. And we have friction, kinetic friction. We know that because they said there's a coefficient, there's some roughness. And then there's the normal force, Fn. And it looks right now like the block can't possibly be going up. Why is it moving up? Because there is a person pushing with 35 newtons directed up along the ramp. Remember, we're imagining tilted axes. 3 of the 4 forces are already on the axes, but gravity has components because it's not on the axis. So let me draw those components in. If the angle of the incline here is 42 degrees, then this angle is also 42. So we have mg cosine 42 and mg sine 42. The x component is opposite the angle. The normal force has to balance mg cos 42 because the block is not lifting off the ramp, it's not going up into the air, it's not accelerating downward into the ramp, it's not crushing the ramp. So these forces have to balance. So we do m times g, and remember it's this down arrow which is cosine 42. When we calculate this value, we get 21.14, and rounding for sig figs to report the answer is 21. The kinetic friction force we get from the mu equation. I've rearranged. Mu we were given in the problem, that's going to be 0.65. And the kinetic friction force is what we found above, this unrounded value. So when we calculate, we get 13.74. Rounding for sig figs to report the answer is 14. The net force, well, there is nothing on the y-axis. All we care about are the x forces. Those are the ones that may not balance. So there are 3 if we look at the picture. 2 point leftward and 1 points rightward. The only force pointing to the right, the only positive x force, is that guy. But then we also have this pointing left and this pointing left. The arrows point down the ramp. So we add those 3 up. We've got positive 35 as the applied force. We've got negative mg cosine theta, mg sine theta, which is 5.2 times 9.81 times sine of, what is it? Oh, I'm sorry, this is 2.9. I'm looking at the wrong problem. Negative 2.9 is the mass times 9.81. Sine of the angle, which is 42. And then finally we have negative kinetic friction because it points down the ramp. So the kinetic friction force is this one that we found above. The unrounded 13.74 ... When we add those up, the net force, which is all on the x-axis, there is none on the y, net force comes to 2.2, 217.81 ... We round that for sig figs, 2.2. The acceleration, we use Newton's second law, F net equals ma. And again, I've rearranged. Whoa! There we go. Plug in the net force from above. 2.217 ... all those numbers. For mass, we know this. Mass is 2.9. And this gives to 2 sig figs 0.77. If we work out this one, it's the exact same. You've got Fn, Fk, gravity, and there's a big applied force. The components look like this. The normal force comes to 42.78. We round to 43 for reporting the answer. The kinetic friction, found the same way, is 12.4 ... We round to 12. The net force, when we add up all the forces on the x-axis, because there are none on the y, the net, well, there are forces, but they just cancel. The net force is going to be 5.8 when we round, and the acceleration comes to 1.1.